Which screen are you guys seeing? Got it.
Fast radio bursts.
Okay. At some reason, I was expecting an outline and it didn't. So it must have been a Zoom update that changed how it told me what screen I'm presenting. Cool. So, welcome. I see a lot of new names this month that I don't recognize, which is always a good thing. For those who are joining us for the first time, welcome. This is the monthly meeting for Tucson Astronomy's Astronomy Fundamentals Special Interest Group. Our normal format, we meet once a month on the second Thursday of the month, 6:30. We generally have one or two presentations. It depends on presenter availability and whether or not we get something interesting put together in time. For this month, we just have the one presentation here. We'll be talking and introducing fast radio bursts to you all. This presentation will be a little bit more on the advanced side of things in terms of concepts from what we normally talk about within this group. Regardless, I still hope you come away with something really, really cool. And without that, if you have questions during this presentation, because there might be some things that I'm assuming you'll have a little bit of knowledge about and may just skip over. Uh, but if you do have questions or need something clarified, by all means, go ahead and ask them either in the chat or open directly. I'm fine with either approach. And with that, and turn on subtitles. So, fast radio bursts. These are a very interesting recent discovery in astronomy. Recent being only within the last 10, 15 years. Before we talk about what they are, we'll talk about what who first discovered them. The first observed fast radio burst was found by an undergraduate student from the University of West Virginia, working under a PhD advisor known as David Lorimer. The student's name, David Narkevic, found the first radio burst while hunting for pulsars and data from the Parkes Radio Telescope, which is located in Australia. The student stumbled across a super intense radio signal that originated from somewhere near the Small Magellanic Cloud. And when they were initially doing hunting for the signals, they weren't expecting to find anything. And on a whim, Dr. Lorimer advised the student just to greatly throw out wild settings in one of the programs they were using and see what they found. And they stumbled across this. So very much one of those just like, huh, weird. We didn't expect that moment. The signal that they detected amounted to dumping out the entire monthly output of the sun in about 5 milliseconds, all in pure radio waves, which, is quite remarkable. When we have talked about in the past of really crazy, powerful, energetic events, the normal things that come to mind are gamma ray bursts, which are similar in nature. They're, highly energetic uh, beams of energy that we see here from Earth in the form of gamma rays. This is the lower energy version of that, where instead of gamma rays, it's pure radio. They originally estimated the source of this galaxy, or this, well, not galaxy, of whatever emitted this radio burst to be about 1.6 billion light years away. And when they were trying to determine if the signal itself repeated, they didn't get anything after about 90 hours of observation. So whatever caused this was, in this case, a one-time event, which suggests something usually a really big explosion. But the nature of the signal and the amount of radio waves left a lot of astronomers puzzled. And we'll talk more about that here in a second. So these two pictures are actually taken from the original paper that published the fast radio burst. Here on the left is a map in the sky of the Small Magellanic Cloud area, which is showing where the burst kind of originated from. So up here in these gray bluish areas, these are hydrogen alpha regions in the Small Magellanic Cloud, which is highlighted by this border zone here. And then down here in these circles, these are the zones of interest that the Parkes Radio Observatory was pointed towards at the time, with the squares in them being the zones in which they detected the fast radio burst from. And over here on the right is the signal that they were able to detect from the radio burst starting here at 5 gigahertz and just to slow down over the course of about 4 seconds. Most of the energy coming out, way up here. So we won't spend too much on this. It's really to see like a year of the actual astronomers in the signal record. This is the left map is really more important. Like, where is this thing? Because when we talk about, sometimes things get first discovered, we generally leave out where in the night sky they actually were. Next, go to the next slide. There we go. So as part of their work, they also set out trying to figure out, what might have caused this really giant burst of energy. And doing some math, they came to a conclusion that whatever emitted the radio burst was less than 1,500 kilometers in size and diameter, which is a slightly large, I think somewhere around the size of Mercury. The long-winded way of explaining how they got there involves using the speed of light and saying, well, if the speed of light left this side of the object and this side of the object, it would affect the signal in this way. And there's a whole bunch of math and like 3 pages of explanation in the paper explaining how they got this. So the short version is speed of light comes into play, and they can measure that with radio waves. The fact that the signal did not repeat, as I had mentioned, suggests that, whatever did this is, a highly destructive event. But because we didn't detect any other light, optical, like we would normally see, or X-rays or gamma rays that you might associate with a supernova or a black hole, kind of leaves uh, kind of a head scratcher. Like, well, what could be causing this? Because supernova and gamma ray bursts are generally some of the more energetic events that might have clued us into as to what was going on. We didn't get any of that. So they also concluding in saying, well, where can we potentially look for these things next? And doing some other statistics analysis, they said, well, maybe we should be seeing a couple hundred of these per year. Keeping in mind that this was in 2007 at the time. And some of we didn't really have some of the telescopes, which we'll talk about here later, available to us that would make searching for these events more practical. Most of the of the radio dishes that we had that were doing astronomy purposes or narrow fields of view. So it was kind of a matter of really just getting lucky and looking in the right place in the right time. So over the next, 10 years, owing in part to, the limited field of view, we'd only been able to detect, 26 more fast radio bursts. But one of these one-time sources, adding to the whole, what's really causing these, threw as much energy at us in radio waves as about 500 million suns. So we've gone from, average monthly output of the sun in 5 milliseconds to 500 million, you know, suns of energy. So a very broad range uh, in terms of output. It's really kind of just like, how do you get this? Been one of the ongoing puzzles. Uh, and as I mentioned, a lot of astronomers, in these early years, as these discoveries were coming in, originally chalked them up to measurement errors or, some other local terrestrial source. This has led to one very, very interesting paper which I'm snippeting here on the right, from Petrov et al., uh, where they basically spent it reached like one of those papers that you would expect from a PhD researcher who lost a bet with another PhD researcher and had to do something, really begrudgingly, or a graduate student that took the short end of an assignment stick. It's a very it's a very cutesy paper that spends 8 pages explaining why something isn't a microwave. Can anyone hear me? My mic just disconnected. Can I get a confirmation?
Yeah,
We
you're
got
back up, Connor.
Okay, cool. That was super odd. My headset just randomly turned off, but the battery is fine. If it happens again, I will switch to a different headset. Was not expecting that. Uh, but as I was saying, so this is one of those papers that really just feels like somebody lost a bad bet. But it's a very humorous read if you're willing to read between like the academic, sternness of it. Uh, the comic here on the left is what tuned me into this particular paper. I just find it very amusing in general. Uh, but as the comment suggests, we eventually started leaning towards a potential cause, not really certain quite yet of what actually is causing them. We'll talk more about some of those theories here in a second. But continuing to fast forward a couple of years, and about 2016, we detected our first repeating fast radio burst. Uh, this burst was dubbed FRB 121102, otherwise generally referred to in some of the articles as the Spitler burst after the primary author of the paper. This was originally found by the Arecibo Radio Observatory in Puerto Rico, which, as some may know, has since collapsed because of age. It was not originally detected by the Parkes Observatory in Australia, mostly because the radio that particular observatory wasn't sensitive enough to detect this event. From what I understood, is the emissions were slightly weaker and fainter, than what Parkes was, or it was on a different frequency, lower frequency than what Parkes was tuned to for its primary emission. With this signal, in the same area of sky, the uh, the Spitler team detected 11 additional bursts during follow-up observations in 2015 over a 2-month period. So we've gone, from having here's this one event, it occurred only once and then never again, finding a couple dozen more of those, and then all of a sudden we have a repeater. Slightly different characteristics in terms of amount of energy dumped at us. It's 10 times weaker than the non-repeating radio burst that we found originally from the Lorimar burst, which is what it has since been dubbed. So this is hinting at, well, maybe they aren't caused by the same thing. Maybe these repeat bursts have a different underlying cause than the non-repeating bursts. But the question then is still, well, how do you create this environment? What's causing all this radio energy? And over here on the right is the coordinates for all of the repeat bursts that they managed to detect. And if you're curious to where that in the night sky is, it's actually located here in Auriga, roughly in these crosshairs. So over here to the top left, we have Messier 36. It's an open star cluster. And then over here to the right, we have IC 410 in this gas cloud. And it's kind of somewhere here around this area here in the center. Uh, however many millions of billions of light years away. They So building on their initial find for these 10 repeating FRB subburst, they went out to the Very Large Array in Chile and said, "Hey, go look at this over more for us, please." And so the VLA team, obliged, and they spent about 6 months of observation time looking in the same region of sky. What's important here is that while they detected 11 more events, there wasn't any regularity or periodic nature to these signals. What this means is that whatever's causing them, there doesn't seem to be two objects orbiting each other in a regular period that would suggest, like, hey, we have two black holes orbiting each other and there's some energy buildup. Excuse me. That would, suggest a likely cause. So there's, we can rule out, some categories of, massive orbiting objects like a star orbiting a black hole or that sort of thing. So we're slowly whittling away our options and kind of coming up with removing all the obvious answers. They put a rough estimated distance for this initially at about 5.5 billion light years. With some later work, and they're finally able, from a different team and some more observations, they eventually whittled that away down to about 3.2 billion light years. And then eventually chased it down to a dwarf galaxy, which was about 12,000 light years in diameter. For context, this is the Small Magellanic Cloud is about 15,000 light years in diameter, so they're roughly the same distance. And the fact that we're able to detect that from 3.5 billion light years away is still kind of phenomenal. This burst outputted about 10 to the 38 joules of energy overall. That was their rough estimate on it. Still, you know, uh, uh, the non-repeater burst was 10 to 39 joules. This is 10 to 38 joules. So, this is still tremendous amounts of energy between the two. And I don't know if this will actually play. This will be my first time trying to do a YouTube video over. I don't know if you'll get audio for this or if it will play. And it doesn't want to. Oh, come on. Don't know if this will be too loud, so I apologize in advance if uh, there is some noise. So what that was is they ended up taking the radio waves from the FRB, the repeating FRB, and they translated it over into audio frequencies that we can actually hear. And if you without ruining everybody's ears and tailing it, you'll notice that the signal, like we saw in that graph, the signal gradually tapers down, getting lower in pitch. Come on, over time. So of the 21 bursts that they've since did, by this point they had cataloged from this one source, they didn't have the same length. Some of them, had dumped had a duration of only about 30 microseconds, some up to 1 millisecond. So whatever it is, there's some irregular process going on here. Uh, excuse me. But while also cataloging all of these, they finally managed to get a measure of their polarization. If you have seen some of the news articles that came out with the Event Horizon Telescope, you may recall that polarization helps tell us how much magnetic field a light signal has passed through. And the exact physics of this I'll leave out because it gets kind of complicated. But what that told us is that whatever is producing these radio signals is coming from a ridiculously magnetic region of space. The authors in it basically said, we've only ever seen this level of magnetism around supermassive black holes, or intermediate mass black holes in this case. So, okay, still really confusing to many. It's like, what's going on? Uh, but in addition to the immense polarization, they were also follow up weaker subbursts. Basically, think of it as after tremors from an earthquake. Aftershocks from an earthquake, you have one large quake, and then over time, you'll have some smaller, weaker subbursts or sub tremors that have orders of magnitude less energy than the original burst. And you know what they were saying is that in addition to these being less energetic, their frequency is also steps down as well. So, telling us, adding more clues here into the environment of what we needed to eventually narrow down to. For kind of a reference as to what they're looking for, this is the polarization image from the Event Horizon team that they published, I think now in 2021. To give you kind of an idea of what I'm talking about with the polarization here, where these this twisting or striations in the light, which they've rendered, for us to see. This is what they're seeing with the radio waves, and that the radio waves themselves are essentially, rotated quite a lot. I think I'm not quite sure how much rotation is in here with the M87 black hole, but I think they were saying it's similar in intensity, with how much they were saying. So now we have, a slew of one-off events, a single repeating event with a whole bunch of with a whole bunch of, individual repeats there. Still not much to go on in terms of figuring out what exactly is going on, what's exactly causing these fast radio bursts. And fast forwarding about 2 more years after the announcement of the Spitler burst, which was published in 2015, the Chime Observatory begins to come online. This is a radio observatory in British Columbia, Canada, whose primary mission was to help measure the expansion of the universe. By the time, excuse me, and by now, we've seen about. Uh, sorry, I'm missing that lineup. So at this point, most of the astronomers, they're just pushing out like, well, what's this? What's this? To trying to fit the small pieces of evidence that they currently had to date, namely, no optical emissions, lots of gamma rays, high magnetism. And, from 2007 to 2017, they had over 50 different theories going on for what might actually be causing FRBs. So they needed more data. They needed to be able to, find more of these events to help narrow down and localize them in terms of finding out where in the night sky they're coming from to get a better grasp about what's actually causing them. And rather fortunate turn of events, it turns out the Chime Observatory became really good at finding fast radio bursts. While it was still under construction, only portions of the array were built. There's multiples antenna dishes, and they'd only built some of the antenna dishes. They were, checking out the instruments, making sure they were all running and doing limited collection runs. And during one of these runs in 2018, they got really lucky and they found a second repeating radio bursts. This one was located near NGC 1560 in Camilo-Pardalis. So this particular repeat is near the region of Polaris, around that portion of that sky. So it's definitely around the northern celestial pole. But conveniently, this one was also measured to be a lot closer. Uh, I think they pegged it, we've gone from, 5.5 billion light years to 3.3 billion light years to 1.5 billion light years. So this one, see, getting closer all the way. But what's interesting is the new repeater also shows the trendward subbursts, these downward trending subbursts. And I do. Okay, cool. I have a chart here on the next page that'll kind of show what I'm talking about a little bit more. And but still continuing on during their instrument tuning, by 2019 they had found close to 500 new fast radio bursts at chime. About 470 of those were not repeating bursts. So so we get immediately, well, not immediately, over the year of observations, that the non-repeats are much more frequent. They are the non-repeats. So whatever is called the repeats, it's definitely much more rare actually. Goes and if you actually are interested, this URL here at the bottom, chime-frb.ca, this actually has a list of all the fast radio bursts that they've cataloged to date. So yeah, I mentioned these sub bursts and sub pulse a couple of times now, and without showing more graphs and things, this is kind of a rough idea. So here, this 2018 is one subburst, and it's showing here, how its frequency steps down from 485 all the way down to 422 megahertz over the course of, many, many milliseconds. I think this is time after the initial burst, and how long that pulse lasted. So this is, 0 seconds. It lasted 11.8 seconds. This started at 13 milliseconds, lasted for 12 milliseconds, and so on. With this just downward trend in frequency, all from the same burst. So it's not so that's you know clarifying the situation when we're saying, well, what's the subburst different from the repeat events? They're in that same window. It's just in incremental steps. Clear as mud. So this is the full Chime Observatory array where and its construction, so they only had to bring on one portion of the array, like this whole right antenna and line, before they could start taking measurements, and eventually over time they completed the whole array. So we have a lot of things to reconcile here with these fast radio bursts in terms of what's causing them. Is it neutron stars? Is it black holes? Some type of supernova involvement, which we kind of have sort of ruled out. Is it due to neutron star mergers? There's a lot of interesting things to consider, and it has to be generally you would think it's either going to involve a really massive star, a really massive black hole, or neutron stars. Really, kind of the only options that we have uh, in order to produce something this energetic. But Hello? You guys hear me?
Got your back, Connor.
Audio check.
Heard you about 20 seconds ago, but about five ago was garbled.
How about now?
Hear you pretty good right now.
Sorry about that. Headset was supposed to be charged. I don't know why it's cutting off on me. It's full battery. With the one that has a wire on it instead. Are we all good? Good audio?
Yeah, a little bit of an echo in the background, so you're not using your microphone. You're using the laptops or your computer's microphone.
Let me. How about this one?
That's a lot better.
Okay. So when it switches to the headset, it's always which one of those, because it just shows like three microphone options without an actual device label. So I don't know which one I'm picking. So sorry for the interruption. So the things that astronomers needed or need to, sort out or include when in their theories is uh, we've seen that since that repeating fast radio bursts uh, aren't related to any orbital mechanics. So there's no two bodies orbiting each other that would influence each other in a way to produce the burst in a repeated manner. The Since each of the bursts and a repeating burst, there different amounts of energy in each burst. There isn't a uniform. This is always X number of joules for a Y period of time. There's some highly irregular and dynamic environment at play. Non-repeating bursts versus now they this differs from non-repeating bursts, which have a much higher energy. So whatever is causing the non-repeating burst needs to come from some sort of cataclysmic event, such as a supernova or some type of supernova or a black hole star merger. But we've already kind of said, well, it can't be a supernova because there's no X-ray or gamma rays, you know, um, and since we've only been able to find some of these events through very large sky surveys, we've had issue finding the exact location of some of the non-repeating fast radio bursts. Versus the repeating bursts, or at least the two that we'd found up to this point with Chime before they found the initial 15. We've been able to localize those pretty well. So finding out what's causing the non-repeats continues to be a challenge. Um, you know, which starts heading towards, it also needs to come in a region of very high magnetism. So this potentially suggests, uh, an active galactic nucleus or a magnetars or a combination of the two. But whatever, if it is a magnetar or how it involves a magnetar, then um, the amount of the strength of the magnetic fields is greater than any magnetar that we've been able to observe. So it's a lot of things to fit here, and they all have to kind of go into play. And since I mentioned magnetars a couple of times, just to make sure that we're all on the same page, a magnetar is a form of neutron star. This is typically a very young neutron star that has crazy high magnetic fields around it. The magnetic fields around a normal magnetar are so intense that it essentially turns into a disintegration ray. It's able to freely strip off electrons around atoms. And so chemistry that we normally think about, which involves the exchange of electrons, can't happen. So if you've ever thought about what a celestial disintegration ray looks like, think of a magnetar. So moving on, we have all these little individual clues that we got to put together, and lots of theories to go around with it. So this, with the magnetic fields, so the first thing we got to do is fit, where do these magnetic fields come into play? And I'm only going to go through two or three theories here, just because these are going to be more on the easily to verbalize and explain side, without going into crazy things, which some of the theories are like, oh, this involves dark matter and crazy exotic configurations and hocus pocus. So hopefully these ones will be a little bit more understandable and digestible. Whether or not these are actually the current trending theories or whether they've been ruled out, I can't necessarily say. I didn't have time to go into, figuring out where some of these theories eventually wound up, or if they're still being considered or not. So these are more of a, here's some of the things that we've thought about. So in one situation, they proposed that for a repeating FRB, you could have a neutron star that is orbiting the supermassive black hole in the center of its galaxy. And this is where the magnetic fields of the black hole somehow end up charging the normal radio waves that a neutron star emits, basically giving them a massive supercharge. This gets, okay, not quite sure how I would see that, but again, I don't necessarily study in depth some of this galactic supermassive black holes. So, you maybe would have a really big combination of, a really big black hole, maybe something like M87 size, which is like 2 billion solar masses compared to our galaxy's 2 million solar masses. So regardless, there's some exchange of magnetism there. The other one other theory was that you have a magnetar that sits within a supernova remnant. So this is a star that just went supernova and has collapsed into a magnetar. And while this magnetar is sitting within this, recently formed nebula, its magnetic field is stripping off electrons from the surrounding gas, even though that gas is expanding at, something like 600 kilometers per second. Building on that last theory, we jumped to a researcher named Brian Metzger. And he came in after seeing the second repeating burst that came out of the Chime Array. And looking at the nebula theory, he came in and said, well, what happens if you get basically magnetar flares? So this is the magnetar equivalent of a solar flare. But instead of, in our case, spitting out, relatively tame streams of plasma, the magnetar is spitting out bursts of electrons and anti-electrons, or positrons, at nearly the speed of light. And so what's happening is that these little flares of energy that the magnetar is throwing off, because they're traveling faster than the shell of gas from the supernova remnant, they eventually collide into it. And I apologize. There's a picture on the next page to help explain this particular theory more, but let me get through some of these words. And so eventually, these repeated bursts, think of it just like building up a lot of static charge onto this nearby nebula, the supernova ring. And eventually, after, however many number of flares that have, been thrown into this nebula, that nebula can't really take on any more charge, much like a capacitor. You can only fill up a capacitor or battery so much, and then it needs to discharge that energy, all that energy. But in our case, it's discharging all this energy as radio waves. Uh, you know, so over here on the left, we have this magnetar. It's ejecting this flare, the laser pointer. Yeah, it's ejecting, this giant burst, of, not really giant. Magnetars are about 10 to 15 kilometers in diameter, which also is matching with some of the size constraints that we were talking about earlier. It needs to be a very small object. So these little essential micro flares of pure electrons and positrons, these are moving outwards. And this represents the shell or the leftover, the nebula remnant of the supernova. So this would be like this. This is, the star in the center of the Crab Nebula, or Messier 1, which is a supernova remnant that you can see during late fall and winter. And then this here is the gas of that nebula, and they just hit. And eventually, electrons themselves confer a magnetic charge. They are, negatively charged at subatomic particles. And so this, collision repeat, these build up magnetic fields inside of this shock front. And eventually there's no more room for new energy and it discharges it. So pretty convincing. I'm not quite sure if there's some subtleties at play here, but it seems like we have a good background cause for what's causing our repeating bursts. Not so much for our non-repeats. But the benefit of Metzger's theory is it at least produces some things that we would be able to observe that during a repeat FRB. We've seen one of them with the subburst with a downward frequency trend. We've seen that he also work says that sometimes you may get X-ray or gamma ray emissions. This really comes into an orientation sort of situation. So with a gamma ray burst, they're essentially just like someone shining a flashlight in your face. But if someone shines that flashlight in a different direction, you're not going to see it. So what he is suggesting is that we may not be seeing the gamma ray or X-ray bursts merely because the radio burst is pointed at us, but the gamma ray bursts are not. So not only that, but he would also expect that we would see these events more likely in starburst galaxies, like the nearby Messier 82, which you can see, tied out in your telescope. It sits in Ursa Major. This is because these stars are actively forming lots of new stars, very rapid cadence, but magnetars are the leftover remnant of very massive stars which don't have very long lives. So we would expect that these starburst galaxies, which will have massive stars form and then collapse in a astronomically quick time scale, we'd be able to that these starburst galaxies will have a larger population of magnetars, and so we might see that there would be more of those events there. And the charge, because the flares on a magnetar themselves don't really have, there isn't a flare like every 3 days or something in the same direction in the nebula, that this would help contribute to the irregular breaks between individual bursts, which we've kind of also observed. So, I feel like we've checked off a lot of those particular options, except for maybe the starburst galaxy localization and the gamma ray and X-ray emissions. But it's, we're making progress. Non-repeating FRBs, well, there's just a lot. There's some there's so many at this point that astronomers actually had to make an entire wiki in order to track all of them, just because there's like a new theory every week that somebody puts out in some academic journal or on archive.org. And so they filter through them and look for them, like which ones seem the most promising or that sort of thing. Uh, and as I suggested, they tend to get pretty exotic. Looking at some of the titles and abstracts, it's just like I understand none of that. Uh, so, but there is one that is a little bit more digestible, and it's what has been come to be called a blitzar. You know, there's a lot of R's in astronomy. You have quasars, magnetars, pulsars, blitzars. I don't know what it is with astronomers in that particular suffix. They seem to like it. But uh, blitzars were actually proposed after as a source for fast radio bursts, uh, kind of on an off chance. Uh, this particular astronomer, Moroniau, I butchered that name completely, uh, was looking, you know, at a gravity wave source, and conveniently noticed that this particular gravity wave is also accompanied by an FRB. And what a blitzar currently it's a very special case of when two neutron stars merge, which we've recently seen, in the last 3 or 4 years with the LIGO and Virgo observatories. We know for a fact that neutron stars can merge. But what makes this a little bit different from the quote unquote normal neutron star mergers is you need the neutron star pair to be on the small side, both stars. And the idea being is that these two quote unquote small neutron stars uh, need to be in the right mass range so that when they merge, they don't exceed what's known as the Chandrasekhar limit and immediately collapse into a black hole. So, and of course, since these two neutron stars are spinning around each other and they're getting a lot of angular momentum to each other. And so when they merge, this new neutron star becomes an even faster spinning magnetar. But it gets a little bit weirder. So it turns out that, like many things that keep our universe stable, the spin that was added to the neutron stars by their merger is just so enough that it keeps the neutron star from collapsing into a black hole. But over time, this magnetar will slow down. And over time, it turns out to be in a matter of hours. And eventually it slows down, and the spin energy that it had can't keep it from collapsing. And it goes, from neutron star merger to magnetar to black hole, all in the space of about 3 hours. And somehow, and the part I didn't quite get from their work is the merger of the two neutron stars is somehow able to clear out any debris around the two magnetars, which would explain, without the debris, there's nothing for black holes to consume. And the only way we normally see black holes is when they consume material around them. And that we normally see is X-rays and gamma rays. So this, may help explain, is certainly an explanation for, why when we see fast radio bursts, we don't get any X-rays or gamma rays. all the magnetic fields have somehow pushed it away, far enough away from the black hole that it just can't grab it in time by the time the black hole forms. And that's kind of all I was able to get together. I'm surprised that took me 50 minutes. Consider that in itself. Um, I hope there are questions because there's a lot in there to digest in a very short time frame and a lot of really weird moments. So I'll open this to discussion or comments. And if you want any of the resources as well, if you want to, if you like reading them on your own time, I do have, 4 pages of references for this presentation. That's not Wikipedia for once.
I got one for you from the first slide where they first discovered the FRP.
Okay, let me get back to that real quick.
No, you don't have to go back in this case. It said they estimated to be 5 billion light years. Any idea how they would make that estimate since it was a completely unknown phenomenon? I'm thinking in the light domain, you have if you know your helium spectrum and it's shifted, that's one way. If you know the brightness, you can compare with C-feed variables. You have things like that, but you have to know something about it.
So
how do you suppose they found or they estimated the distance?
there are 2 ways that they go about that, and that's a great question. I kind of left it out of this mostly because I didn't. It gets kind of. I didn't have a good way to put it in like succinctly. So there's 2 ways. One of them is redshift, which since any form of light, which radio is a form of light, will be redshifted by the expansion of the universe as it travels through it. The other way, and that applies specifically to radios, is what they term the dispersion measure. The the short way to put it is it's basically they look at as the radio waves travel through space and they pass through gas, this alters the radio waves in a specific way. And the more gas and interstellar medium and intergalactic medium that the radio waves pass through, the larger the dispersion measure of that signal. And so that's one way that they are able to use radio waves to get a distance measure in addition to redshift. I don't really have a really good confidence on explaining the physics or mechanics behind the dispersion measure and how that gets measured. So that's why I left it out. I didn't want to, but good question.
That's good. That's a good answer. Thanks.
Pete,
Hey,
you're off.
Connor's Pete.
Yeah.
Hey, sorry, my Wi-Fi wigged out, so I just came back in. I take you're taking questions now.
Yes.
Okay. Hey, one basic question I had: Are there any? And I didn't see anything, and I might have missed it. Are there any optical or visible events that have occurred that coincided with any of these bursts that have been noted, or is this strictly radio or other wavelengths that we would normally see optically?
To my knowledge, there hasn't been an optical X-ray or gamma ray component, but
Okay,
there has been one that has had a gravity wave component.
right. Yeah, I remember you mentioned that. Thank
So
you.
mhm. Is one of the things that makes them kind of this giant confusion to observe is, you only get radio signals. And we don't have as many radio telescopes as optical scopes out there. So any more questions? Any more comments?
Just one comment. I don't know if you mentioned it earlier and not related to your topic, but there's a Falcon launch out of Vandenberg at 8:20 our time this evening, or at least the first opportunity.
Thank you, Pete. I did not know.
So maybe might be a pretty good show, but they've got to basically they've got a 2 hour window. So, but their first opportunity, and it's still current on the website, is 8:20.
Thanks for
Uh,
noticing that. There's so many of those, I typically just ignore them. They do like a launch every 3 days from somewhere.
Yeah,
But
I know,
no,
but it was just like when we saw that one out at Temple last month. I mean, that was the first one I've seen in a long time, and that was pretty impressive.
yes, they are.
Thinking about how high altitude off the horizon. I have some Tucson mountains blocking my view. I'm wondering
They
if I'd
get
be able to
pretty
see it.
far.
Yeah.
Here, I'll show you here in a second. No, come on.
I mean, last
Actually,
time we
I
saw
have a
them,
picture that I can show you to give you an idea of what you're looking for, Tom.
and they went from the west all the way to the south over a few minutes. So it was a pretty impressive show. And I would say probably, upwards close to 30 degrees above the horizon.
That sounds about normal when this
Yeah.
website decides to load.
I mean, if you're right at the base of the Tucson Mountains, it might be problematic, but if you got a little distance, might still pick something up.
And for some reason, this website's not wanting to load for me. I have a picture to show to give you an idea, but it doesn't want to render. I don't know why. Anyway, so with that ending this month's topic, I don't have any topics lined up for next month. I'm open to suggestions because, frankly, I'm running out of ideas. Does anybody have something that they would like to see or learn more about? Be happy to do it.
I do have a question about the presentation.
Mhm.
Awesome stuff, by the way. I'm curious if I'm understanding correctly, it sounds like if we did detect a fast radio burst without a gravitational wave accompanying it, that would rule out the Blitzar theory. Have there been any cases of that, or would it just be, for some of them, I imagine the gravitational waves would be too faint to detect?
So it doesn't necessarily just rule out the Blitzer burst. What would happen is that it just means that the Blitzer burst is, one potential cause for, because we've seen one that has gravity waves in an FRB. So that doesn't rule that out. It just means that when we see a non-repeating burst, that there's more than one way that we can get a non-repeating burst.
Okay. I got it. Thank you.
Here we go. It finally loaded. Come on. So this, Tom, when it snaps into place, come on. So this was a Falcon Edge launch that I saw in mid-March to give you kind of an idea of what you're looking at. It looks like you almost think it's a comet really close that just appears in the eastern sky all of a sudden. Is my screen still sharing?
Yeah, it is. It
Okay.
looks good.
Yeah, that's cool.
So this was taken from around River and Campbell to give you kind of an idea. So the mountains so the Tucson mountains are behind these bushes. But with the altitude it goes to, you might, if you're really close to the Tucson mountains, like over on like the west side of I-10, you might not see this lower right portion of the image, but you'll certainly be able to see this upper left portion in terms of like the expanding cloud from the rocket exhaust as it progresses through the atmosphere. And this is going from north is on the right to south is on the left. And it'll be out of the west. There.
Cool. Thanks. I'll go look.
Cool. So I'm not hearing any topic suggestions. So I'll.
Well, I know we still got more astronomers we could no doubt do. I think it's a matter of recompiling the list of what's been done and what's hasn't been done. And the same thing I think goes for certain other topics that we've covered. We covered the observatories, I think, too, but not necessarily all of them. I know that Stephen had a pretty good presentation on the larger scopes, but I can't think of anything else right offhand.
I think we've, at least from um, our perspective, it might just be go back through some of the old material and represent it again, stuff that we haven't seen in 5 or 6 years.
Like starting to go through the constellations again.
For main topics, we still have plenty of astronomers that we could potentially do. It's
Oh
just,
yeah.
from like a main topic of like what else could we talk about besides an astronomer, and have people come in. You know, so we can chat, Pete, between you, me, and Doug over email.
Yeah, and I'm going to pretty much be out, as far as making a presentation until fire season's over
Oh,
because my
right, yeah, fire.
reliability, other than that, once we hit around to September, yes, I'd be more than willing. And, I have a tendency to try to focus on some of the Astronomical League programs as far as providing a framework for a presentation. In fact, I'd even consider one. I know that Gus, I think a couple of months ago, talked about binoculars, but more or less focusing on some of the programs that were in the binocular program, in the binocular grouping master group for AL. And, I might consider that as a presentation, which would be a pretty good brief to cover about 10 different programs.
Yeah, I don't do a lot of stuff with binoculars, so that would definitely be something. I when you have time out of fire season to put it together, I think that'd be a really cool topic.
Yeah, it's more or less, an experience thing, which I think, some of these presentations that we've had over the past couple of years